Hello, congrats again for finishing your second assignment. You should be very proud of yourself. This is gonna be actually the last video that I'm gonna make in these V3D tutorials, at least for now, And like I said, if you have any questions, if you get stuck with any specific codes, or if you want to learn more about it, you can always reach me by email. Or if you are at the Biomechanics Research Building, you can reach out to the MOVAN or um, fellow students who know more about Visual 3D if you need like a fast help. Alright, so this is gonna be the answer for the second assignment on how to calculate torques about the center mass. So obviously, if you're watching this, I assume that you know how to calculate torques about the center mass, and if you don't, I gave you like specific instructions. But to calculate it biomechanically using kinetic data, I just basically take the cross vector between the ground direction force vector and between the r vector, uh, um, the moment arm vector, which is the vector between the center pressure and the center of mass. And this is while you calculate the torques about the center of mass, but you can calculate torques like joint torques, like for the ankle and so on, and then you just use the moment of inertia for the for the specific joint. Okay, so this is what we're gonna use, but you need to know first is that when we calculate the torques in the sagittal and frontal planes, the cross product of two vectors cannot be those vectors can't be 2D vectors, they have to be 3D vectors. So that's what we're gonna do first. And again, also you have to separate these by walking north or walking south, because if you know the right hand rule, clockwise rotation is negative, and counterclockwise rotation is positive. So depending on what direction you're moving on, it's gonna be opposite. And also depending on um, depending on whether it's frontal or sagittal, you have to make sure that your results uh, are always giving you that same direction. So you want, basically, when you want to run your statistical analysis, doesn't matter whether they're walking north or south. You want to run the analysis on all the trials and all the participants with the same values, given that when it's positive in the frontal plane or when it's positive in the sagittal plane, it means that it's uh, um, when it's positive, it means that it's going counterclockwise, and when it's going counterclockwise, and when it's negative, it's clockwise. So that's what we're gonna do here first. We already did create those tags from the previous video of either walking north or walking south. And then, because I'm running these torques for all the force plates, and I'm not using these first two force plates that we have for the treadmill, so to save me time, I'm running a for loop, and by now you should know how to run a for loop. So I started the for loop and I gave it a name of FP, and I ran this for loop on all the force plates, and that's because I created this for a very large data set. So maybe in certain trials, like, they didn't actually go into one of these force plates, so maybe like they only use, like, for example, in this trial they only use force plate 3, 4, 5. Actually, they did use some of this force plate. So another like trials that probably, like, sometimes they use only these 3 force plates, sometimes they use like all of the force plates, sometimes they use this and a few of these. But I ran this for all 4 plates, and if there's no data in that first plate, it will just give you an error. It will not calculate it. But when you have data, it will do the job. So I created the for loop to save me time, and then we started calculating the r vector, so the moment arm. So we have the moment arm, creating this in the sagittal plane. So what we do, again, like I mentioned, because you can't run a cross vector between two 2D vectors, we need to create 3D vectors, but we remove the x value here because we're calculating the sagittal plane. So we give the x values 0, and then in the y value we're just basically subtracting the center of mass from the center of pressure. And if you remember, like the downsampling, when you run analysis on, when you calculate like the difference between a kinematic and a kinetic vector, it will downsample it automatically for you. And also, if you do the cross vector between a kinematic and a kinematic, between a vector that has a sampling frequency of motion capture and a vector that has a sampling frequency um, of a kinetic, then it will automatically do that for you too. But if you want to downsample it yourself, I've shown you the ways to do that. If you want to do that, make your life easier, you can do that as well. But here's what I did. So basically, in the y vector, so I gave a 0 to the x vector because we're calculating this moment arm in the sagittal plane. So in the y vector, I basically subtracted the center of pressure from the center of mass. And again, like I showed you, like it always has to start from the center of mass minus center of pressure. So we're doing that, but we're doing that in the y because we're calculating the sagittal plane, and then the force plate, and then we do the same thing for the z. So for this specific vector, it's gonna be the moment arm again. So we're just basically subtracting the center pressure from the center of mass in both the x and both the y and the z. And we'll do the same thing for the frontal plane as well. Actually, no, I went ahead and calculated the um, yeah. So first of all, let me go back here to show you something very important. So when you run a for loop, like I mentioned in one of the previous videos, so you see like vector on then open brackets, the x value I gave it a 0, and then the y value I did this. But uh, when you replace the force plates with the name that we gave it, you have to give it the add sign. So we start with force plate, center force pressure. So that's the center pressure type, and then two colons, and then original, and then two colons. And if you don't use for loops, you just here like add the force plate number. But when you use for loops, you add an add sign, and then two colons, and then the force plate, whatever name you gave it. I gave it a name of FP to replace those force plate numbers. And again, and then I chose a specific axis of y, and I chose all of the first all of the rows within the first column, given that it will calculate that, it will downsample it for me, but it did not. So I kept it that way. Either ways, it doesn't matter because we're subtracting the center mass from the center pressure. So I can take this off and it will give me the same results. And then we did the same thing for the center of mass z minus center pressure z. Okay, so we did cover that. Center pressure z, it's usually 0, but I put that there. I don't want to like just keep the center mass z, so like the height of the center mass, but calculate it, you never know. Okay, all right, and then after that we're calculating the ground direction force vector, but we're only using the sagittal plane for force vector. So again, we create a vector, and then we given 0 to the x value, the x coordinates, and then we calculate and then we add the y and z values of that ground reaction force vector for each force plates. Again, you know, um, we separate the FP with the add after the two dots, and then as far as I tried, you also have to give a space after you add the second add sign. So you add like force original, and then you replace this value with the FP, so it's gonna be like FP3 first for the for loops, and then give it a space. Don't keep it like this, just give it a space. As far as I tried, it only works like this, and I do the same thing here. But if it does work for you without adding a space, just keep it like that. As long as it works, that's the main thing. Alright, so now we have that force plate F sagittal motion capture hertz. Although, like I said, you know, it actually does not work, so you can take this off. Whether you add like all the rows and the first column or not, it's still gonna see like the x and the y and all of those specific values as one column, like I mentioned in one of the videos before. So it actually does not downsample it this way, but it doesn't matter, you know, like if you keep it or not. But if you do want to downsample your data, you can do it in one of the three ways that I showed you, or you can keep it like this, and then once you run the cross vector here, it will do that for you. As far as I last checked, um, but I could be wrong. So let me double check actually now. Kinetic T. Let me see. T F3. Yep. So actually, like I said, you know, when you take the cross product between the other vector that is in motion capture hertz, and when you take another vector that is not in motion capture hertz, it will automatically downsample it for you. So you know, you don't necessarily need to like downsample it if you're gonna use a vector that has a motion capture value. Like you're gonna do this, you're gonna use the center of mass, any kinematic data, it will automatically downsample it for you. Okay. So the thing that I wanted to show you here is that in the sagittal plane torques and in the frontal plane torques too, north, when walking north, I gave it a -1. So I actually flipped the signs because the signs were not correct. If you just keep the cross, it will give you opposite signs for both frontal and sagittal planes. And the reason I did that is after, like when you run your calculations, like technically and theoretically, it should be correct. You should not need to flip the signs, but because they're walking north, and the signs are like this. So when you look at it from the front, the z is going up, the x is going laterally, and then the y is going this way. So it's like this actually, which when you look at it like front, it will be like this. So when you look at it this way, clockwise rotation will be negative. So when they walk, when they're rotating like clockwise, it should be negative, and when they're rotating forward, like here, when you look at it this way as well, it's gonna be like this. Um, when they're rotating forward, that's clockwise, so that should be negative. But when we don't give it a minus sign, it gives us the opposite direction. So that's why I gave it a minus sign. Also, here, the way you calculate the torque itself is just very simple. You know, just take the cross product between both vectors. So we take the cross product. Cross gives you the cross product. Again, like I showed you, you have to read the whole expression in Visual 3D. I don't have it here, but you remember, like I showed you that. So if you just go to see motion, expression, and here will give you all the expressions that you need. So when you type like cross, it will tell you like creates a cross product between of A and B. But the A and B vectors has to be 3D vectors, not 2D. If you just only add 2D vectors, it will not. It will give you an error. It will not read it. That's a rule in physics and trigonometry and math in general. It's a mathematical rule. So you always have to have 3D vectors to get the cross product. So we get the cross product of, and then we open a parentheses. So you get in the that moment arm vector, which is the vector between the center of mass and the center of pressure in the sagittal plane, and you get the cross product between that vector and the ground direction force vector in the sagittal plane. Once you get the cross product, then you're gonna get the torques. So it's pretty straightforward, but you have to make sure that your signs are correct. And then I basically calculated the mean. So you have metric mean will give you here, it generates a mean value of a signal as a metric. So I got the mean of all the torques within each force plate. You can do that. You can just skip it. I just did it, but either ways, if you're gonna run your statistical analysis later on MATLAB or usually in MATLAB, you can do all of these analyses later on. What I usually do is like once I export all of these FPs, I all of these torques within each force plate, I actually like sum them all. So you see like the time is the same. When they're not stepping on one force plate, they're stepping on another force plate. So when I get the sum of all of those, you get like clean torques about the center mass from all the force plates. Okay, and then I also got the standard deviation. So you see that like metric standard deviation will give you the standard deviation of any signal you want. So I got the mean and standard deviation of both frontal and sagittal planes for all the force plates, and then I extracted the global minima and global maxima of each of these measures as well. So like extracted the global maximum of the sagittal plane and the minimum of the sagittal plane, and then also the maximum of the frontal plane, and then the minimum of the frontal plane. And then I extracted those values from those events. We should be very familiar with these processes. And that's what I did. So I'll save it. Actually, you know what? I'll save it for 2. I'm gonna run everything, and you'll see here everything is fine except for like I showed you. So here we have FP7. Any force plate that does not have signal. So here it says error, no signal was found to create metric, and you don't have a signal on any of these force plates, it will not calculate it. But doesn't matter now. Like either ways, and calculate everything else that has a signal. So we do that for the Walken North, and then let me save this, and then let's add the Walken South calculations, and then we'll execute this pipeline as well. And also will give us errors. So it gave us 10 errors, and that's because we don't have data from FP6, FP7, FP8, and FP9 and FP10. So in this specific trial, like if you see here, the first one, they only stepped on force plate 5, 4, and 3. That's it. They didn't really touch any other force plate. So okay, so with that, here is the same calculations really, except for the cross vector. We only needed to flip the signs of the sagittal plane, but the frontal plane signs are good. And again, like I told you, you always have to double check your data. So if you remember, like when we used the cross product, we basically skipped the x for the sagittal plane and we skipped the y for the frontal plane. So when you calculate the, for example, like they stepped on the force plate 5 first. So when you go to force plate 5 sagittal, you see here it gives you the cross product of the like the x, because it's sagittal, and because we got the cross product between these two. So when we go here, we actually calculated the cross product of the R sagittal motion capture, which is um, FP5 R sagittal. So you see it's only an X. It's missing X, S, Y, Z, plus the force sagittal of FP5, which is the same thing. Will have only values from Y and Z. So it basically gives you the cross product in that missing um, axis. So it's X. So it's gonna give us the values in X. So when we look at the values in X here, you see when they're walking south, because we flipped the sign, now it makes sense. So the torques, basically when they produce ground direction forces in front of the center of mass, that gives you backward torques. So now when you look at the Z, Y, and X, when it's clockwise rotation, it's negative. So here they're producing backward momentum, and they're producing clockwise rotation, so it is negative and it's correct. And now whether they actually cross this threshold when the ground direction force here crosses the threshold of the center mass and the center mass lands in front of the ground direction force, that they start producing um, like counterclockwise rotation, so forward rotation, which is positive value. So makes sense, correct. Like I told you, always make sure you check your data. So when you look at the frontal plane, and you look at it from this way, and again, because we took the cross product between the x and z, so the results get we have the results in the y-axis here. So when they land on the force plate, you see like the ground direction force is is lateral to the center mass, so it's basically producing clockwise rotation again. When it is producing clockwise rotation, here it is negative. So again, you look at the you look at this, like the axis like this, and it's rotating clockwise, so it is negative and it's correct. And now when this ground direction force vector briefly lands like contralateral to the center mass, it produces just briefly counterclockwise rotation, and so it goes up to the to the positive, and that's why you have positive. So it makes sense, and it's correct. And then when we go and look at the um, Vulcan North trial, so when we look at force plate 3 here, we look at the sagittal plane. They briefly landed on the center. So basically here, when they land, the when you look at using the finger rules or right hand rule, you can either do it this way. I like to do it this way because it shows us like all the three axes, but some people like to do it this way. This is the right hand rule, and then but I like to do it this way because it gives me all the axes. So I can like just put the axes here. So I have like the x, y, and z. This is the z, this is the y, and this is the x. So when they're producing counterclockwise rotation, which is backward, in this case it's positive, and when they're producing clockwise rotation, it's negative, and it's forward rotation. So it makes sense. When you look at the frontal plane, it's the same thing. So when you look at it this way, um, when the foot lands here, they're producing clockwise rotation, so it's negative, and that's what we're seeing here. Actually, let me go back to FP3. So that's what we're seeing here, like negative, and then when the trailing foot lands, they like now the ground direction force vector crosses the center mass threshold and starts producing counterclockwise rotation, so it starts producing positive values, and that's what we see here. So it does make sense. So once you make sure your calculations are correct, then you can go ahead and start mass producing biomechanical analysis results, and then you're confident with your results. But even then, like try to make sure that you double check all of your data, and if it doesn't, for example, if you run statistical analyses, doesn't make sense, then go back to your data and make sure you have everything correct as well. It's a tedious and hideous process, but better safe than sorry, like, because once you publish your papers, you can't go back. I mean, you can, but it's a long process, and you don't need it. Just make sure you publish your data and you have everything correct from the beginning. It will save you a lot of time and a lot of headache. All right, so those are basically the calculations. Thank you so much for listening. It was a pleasure making all these videos. I know I spent the last 6.5 years in the BRB at the Biomechanics Research Building. It's a pleasure to give back to the department. I've learned all of this from practice and from mentorship and mentoring as well, being mentored and mentoring. So always there, it's always the best way to learn is by teaching. So that also helped me a lot. But obviously, I've received a lot of help throughout the years from my mentors, whether those like PhD students or um, professors or staff. It's just so grateful and so thankful. So I hope this helps or gives back a little bit. And again, if you have any questions or if you want any help, always reach out to me by email. Well, thank you so much. I hope this helps, and good luck.